Uh, Good morning, everyone. Welcome to today's class. Last time on Monday, I went through the exam two questions. I hope that lecture uh, can help you to finish the exam two. And again, any questions regarding the exam or the homework, please let me know. In today's class, we're gonna continue on digital circuit, chapter number 7, digital circuit. And in today's class, we're gonna talk about sign extension and talk about how to do the binary operations such as summation and subtraction. Okay. All right. Last time, actually, on the last Friday class, we talked about there are two type of binary numbers, right? Actually, we use these two types in decimal numbering system too, which are positive, positive, and negative binary numbers, right? We mentioned that to represent a positive binary number, we have few steps to follow with, right? The first one is we write the unsigned binary number. You first write the unsigned binary number, and in the second step, you just need to add 0 in front of the unsigned binary number. Right, just that easy. For instance, if you want to write what's the binary representation of positive 12, this decimal number, right? You want to find what's the binary representation. To do that, the first step, you write the unsigned 12. So unsigned 12 is to convert a decimal number to binary number, you use the repeated division by 2, right? So repeated division by 2 method to find the binary representation. So we divide 12 by 2 and we have result is 6 and remainder is 0. 6 divided by 2, result is 3, remainder is 0. 3 divided by 2, result is 1 and remainder is 1. 1 divided by 2, result is 0 and remainder is 1, right? So the binary representation of 12 is 1100, correct? Alright, after we have the unsigned binary number, and the second step is very simple. We just need to add 0 in front of the unsigned binary number, and we get the signed binary number, and that is the positive sign, right? That's the positive 12. Right, so that's how we handle this process. And in this step, there's one quick way to convert the decimal number to binary number. I want to mention here. That method is called 8421 method. This method actually is very easy to operate. Yeah, first you draw 4 separate short lines. Each line represent a digit, right? The first digit, if you write 1 in the first digit, then in the decimal, that represent 8. If you write another one in the second digit, then this number represent 4. And this digit, if you write 1 on this digit, then in decimal system, that represent 2. And if you write the last one in the last digit, then this number represent 1 in decimal numbering system. So if you write 4 ones, these are binary. The bottom are decimal. Okay, so if you write 4 ones on these 4 short bars, then in decimal that is 8 plus 4 plus 2 plus 1. So that should be 15, right? If you just write a single one in the first digit, and write all zeros on the other digit, right? Then that represent 8. Since on the second digit, it is 0, which means there's no decimal 4 in this binary number, right? So that should be 8 plus 0 plus 0 plus 0. So 1000 represent 0, right? So by using this method, we can quickly find the binary representation of a decimal number within from 0 to 15, right? For instance, if I want to write 11, 11 equals to 8 plus 2 plus 1, right? So the binary representation should be, you write 4 bars, 8, 4, 2, 1. In the binary representation, that will be, we have 8, we don't have 4, we have 2, we have 1, right? So the binary would be 1011, right? So by using this method, you don't need to do the repeated division by 2, but you can use the repeated division by 2 because this method is always correct. But 8421 method is a quicker way to find the binary representation if the decimal number is within 15. Okay. Alright, so that's one trick I want to mention here. So that's how we represent a positive number. How about a negative number? How to represent a negative number, right? We also have a few steps to follow with. The first step is you write the positive number, right? The second step is we flip bits of the positive number, right? And the third step is we add 1 with the flipped number, right? So I also want to use a simple example to show you guys how to operate, how to do this process. All right, so in this example, we try to write positive 12. So in this example, let's try to write minus 12, this decimal number in binary representation. Okay. So first step, we write the positive 12. What's the representation of positive 12? That will be 0, 1, 1, 0, 0, right? The result we find in the previous example. All right, and then the second step we want to do is we want to flip the bits. Flip the bits means whenever you have 0 in a digit, you change that to 1. Whenever you have 1 on a digit, you change that to 0. So basically, it's like flip a coin. Coin has two sides, right? If the coin is one side toward you, then you flip that to the other side. If it's the other side towards you, then you flip that. That would be one the other side, right? So the same idea can be applied here. If the original bit is 0, after the flip, the bit becomes 1. And if the original bit is 1, flip that, that becomes 0, right? So here, after the flip, we have 1, 0, 0, 1, 1. That's the result for the second step. And for the third step, we just need to add 1 with the flipped bit. Here, we need to do the binary number summation. We will talk more about this topic in today's class. But here, let's just do the the simple summation. Binary summation is pretty similar to decimal summation, right? Whenever you have a number or value is greater than 9, then we have an increment to the previous bit. This idea or this principle also applies for binary summations, because the principle becomes whenever you have a value larger than 1, then we have an increment to the previous bit, right? So here we have 1 plus 1. In decimal, that equals to 2, no problem. But here in binary, 1 plus 1 is equivalent to 5 plus 5, right? If you have 5 plus 5, the result is 10. But in decimal number system, there's no a single digit can represent 10, right? To represent 10, we at least need 2 digits. We need 1 0, right? The same idea for the binary numbering summation. If we have 1 plus 1, the result would be 1 0 instead of 2. Okay, so here we have 1 plus 1, we have 1 0, which means we have an increment for the previous bit. We write the increment on the top of the previous bit. And then we have another 1 plus 1, right? The result is again 1 0. So we have an increment to the previous bit, and the result is 1 0. Is 0 for the current bit, for the current digit. And here we have 1 plus 0, the result is 1, the increment is 0. 0 plus 0, result is 0, increment is 0, right? And here we have 1 here, right? So the result is 1 0 1 0 0, right? So that's how we represent minus 12. So some people may ask, how can we verify our result, right? The simplest way to verify your result is convert the negative binary number back to the decimal number, right? The converting method is the same that we used for unsigned binary numbers, but there's a little bit different. For negative binary numbers, the first digit represent minus 1, right? Because this is a signed binary number and this is a negative binary number. So, and then the remaining procedures are same with the previous unsigned converting method. So we also need to count positions of each digit, right? Starting from right to left and starting from 0. So positions of each digit is 0, 1, 2, 3, 4, right? So they are minus 1 times 2 to the power 4 plus 0 times 2 to the power 3 plus 1 times 2 to the power 2 and plus 2 zeros, right? So that equals to minus 16 plus 4, that equals to minus 12, right? Which is the same value before the transformation, right? Alright, so that's how we represent positive and negative binary numbers. That's also a quick review of what we have learned in the last week. And at the beginning of today's class, I want to talk about the sign extension. Okay. Sign extension actually is a very simple idea. For instance, sometimes the question asks you to write a 8-bit signed binary number. Okay. For instance, let's just use minus 12. This example that we used in the previous topic. Minus 12, that equals to 1 0 1 0 0, right? We don't need to draw the line. Okay. Minus 12 equals to is equivalent to 1 0 1 0 0 in the binary number system. But as you can see, the length of this binary number is 1 2 3 4 5. is 5-bit, right? If the question asks you to write an 8-bit signed binary number, then we just need to extend a negative binary number. We add ones. So what that means? That means if you want to write a 8-bit minus 12 in let me put it this way. If you want to write minus 12 in 8-bit signed binary number, the result would be we first write the original representation, right? And that is 10100. And the difference between 8-bit and 5-bit is 3 bits, right? So we just need to add 3 ones in front of the original binary representation. And the result is the 8-bit signed binary number. And the first ones are sign extension. Is due to sign extension. Okay. So one critical question some people may ask is, will the sign extension change my binary value, right? Because if you just look at these two numbers, the first representation, the 5-bit representation is 10100, and the 8-bit representation is 1111010. If you just look at these two values, if you just look at these two representations, you may think these two numbers are actually representing two different numbers, right? But in fact, they are both represent minus 12. So the first one, we actually is very confident with that part, right? Because we did that in this example. So we know 10100 is minus 12. But how about this one? Well, this number also represents minus 12. To figure out this problem, we need to convert this binary number back to the decimal number, right? So how to do that? The method is the same that we used before. So 10100, we need to convert that to decimal number, and the method is the same. We count positions of digits, and starting from right to left, and starting from 0. So the positions of each digit is 0, 1, 2, 3, 4, 5, 6, 7, right? And the first one represents minus 1 times 2 to the power 7, plus 1 times 2 to the power 6, plus 1 times 2 to the power 5, plus 1 times 2 to the power 4, plus 0, plus 1 times 2 to the power 2, plus 0, and plus 0, right? So that equals to minus 128 plus 64 plus 32 plus 16 plus 4, right? And if you do the summation for all positive numbers, that equals to the first two sum together equals to 98, right? And these two sum together equals to 20. And if you sum these two guys together, that equals to 96. 64 plus 32 equals to 96. And then the result is 116. And then you can sum minus 128 and 116 together, and that equals to minus 12. Okay, so one important conclusion for sign extension is sign extension will not change the original value. Okay, won't change the original value of the binary numbers. So in this example, we showed how to extend minus negative. We show example of how to extend negative binary numbers. But how about positive binary numbers, right? This is the punchline. Let me highlight it. How about positive numbers? So give you another example. Positive 12. Okay, positive 12 is 1 1 is 0 1 1 0 0, right? It's also a 5-bit. It's also a 5-bit signed binary number. So to extend a positive binary number, we add 0 in front of it. Okay. So for instance, this number is a 5-bit unsigned binary number. It's a 5-bit signed binary number, and also it's a positive binary number. We want to extend it to 8-bit. Then we just need to add 3 zeros in front of it, right? And this becomes a 8-bit positive 12, right? For positive numbers, because we are adding zeros in front of a binary number, so of course adding zeros won't change the original value, right? Because you are not adding external values to the original number. So sign extension will also not change or will also not affect the original value of the positive binary number. Alright, so that's the sign extension. If you have any questions for this part, please let me know. Okay. Alright, after sign extension, let's talk about the synthesis of logical circuits. Okay. So sometimes, if we are given a specific given a specification for a logical circuit, in a logic expression, and we want to find a practical implementation. So that's the definition of the synthesis of logical circuits. So what that mean? What does this sentence mean? Given a specification for logical circuit in a logic expression, find the practical implementation. So for instance, if I tell you F equals to A times B, okay? F equals to A times B is a logic expression, right? It's a logic expression. Can you find what's the practical implementation of this logic expression? The answer is simple, right? We just use an AND gate to do this job because we have A times B, right? So we have two inputs, A and B. The output is F, and that is the output for AND gate, right? So this together, this is the synthesis of a logical circuit, right? This is a very simple example of uh, of a realization, or the practical implementation of the logic exploration. But sometimes the logic exploration can be very complicated, right? Um, for instance, sometimes the logical circuit could be F equals to ABC plus A bar BC plus A B bar C plus A B C bar, right? For that case, of course, you can also find the logic exploration. You can also find the practical implementation for this logic exploration for sure. But you need to draw a very big diagram, right? So, is there an easy way to find the logic circuit of a logic exploration, right? So here in this topic, we're gonna introduce how to do this job. Okay, let's give an example. If we are given a truth table, and this truth table has two input and a single output, let's use F as the output. Okay, this the truth table of this output is for two input. How many rows for the truth table? If you forget what's the definition of truth table, truth table lists all possible combinations of input, right? If you have two inputs, then you have four rows in the truth table because there are four possible input combinations, which are 0, 0, 0, 1, 1, 0, and 1, 1, right? So the corresponding output is 0, 0, 1, 1. Let's say that's the output of the truth table. Okay, so according to this truth table, can you find the logic circuit implementation? In other words, can you draw a logic circuit such something like this one that represent the output F, right? Uh, if you are given a truth table, some people may ask, truth table is different with logic exploration, right? But in fact, these two things are equivalent. Once you are given a truth table, the logic exploration is also given, right? So why I say that? Because if the truth table is given, then all characteristic of this logic exploration or this logical circuit is given. For instance, if you look at rows that output ones, then you can write the logic exploration of this truth table. F equals to A B bar plus A B. You can verify that by plugging an arbitrary row. Let's plug in the first row. A equals to 0 and B equals to 0. Let's find what's the corresponding F. F equals to A times B bar, right? So A is 0, so it's 0 times B bar. B is 0, B bar is 1, plus 0 times 0. That equals to 0, right? Which is identical to the first row, right? So some people ask, how did you do that thing? How did you do this job? Why can you write F equals to this? To write the logic exploration according to the truth table, you just need to look at rows that are outputting ones, right? In this example, we have row 3 and row 4. These two rows are outputting 1. Then you just look at what are inputs of these two rows. For row 3, inputs are 1, 0. For row 4, inputs are 1, 1. And whenever you have 1, that will represent the original input, which means it's A. Whenever you have 0, that means you have the flipped or the opposite of the original input. And in this case, we have 0 in B, which means we have B bar in the logic exploration. Okay? Okay? So that's how we find the logic expression according to the truth table. And this process can be summarized in few steps. Let me give you these procedures. So the first step is how to write a logic expression according to a truth table. Alright, so the first step is we focus on rows that are outputting ones. Okay. And in this example, we have, if we numbering these rows, let's numbering them from 0. Okay. And the first row is row 0, row 1, row 2, and row 3. Okay. In this example, we have row 2 and row 3. These two rows are outputting ones, right, in this example. All right, the second step is we write a logic product of inputs or input inverse for these rows. Right. So in this example, row 2, we have two inputs, 1, 0, which means if you have 1 on input, that is the original input. If you have 0 on input, then that is the input inverse, which is B bar, right? And for row 3, we have 1, 1, 2 ones, right? Which means we have two original inputs, A and B, okay? And that's a logical product. Let me highlight. That's the logical product, right? So it's A times B bar and A times B. All right, the third step is the output is a sum of products. It's a sum of products, right? And sum of product can be summarized by 3 letters, or can be a derivative by 3 letters, SOP. Okay. So the output F equals to AB bar plus AB. Okay. Alright, so why we need a logic expression? Because after we have the logic expression, we can draw the logical circuit, right? So we have A, B bar. If you have two inputs, A and B, the first term is A times B bar. So we need original A, we need B bar, and we need multiply them together using an AND gate. And then we have A times B, which means we just need the original A, and here we have a dot here, which means these two lines are connected together. We also need B bar, and also connect these two lines together, right? And then, I'm sorry, I made a mistake. For the second term, we just need B, right? Because the output is A times B. And then we just need to sum them together, and the result is AB bar plus AB, right? That's F. Okay. All right, so that's how we find the logic expression and how we find logical circuit implementation according to a truth table. And this method is called sum of product. And in the next class, we're going to talk about how to summarize, how to simplify logic expression especially the sum of product expiration by using by using the kernel map. Okay, and after the next class, we'll pretty much finish this chapter and finish this class. So before the final exam, for this semester, the final exam, I didn't look it up the exact date, but I estimate it's about at the end of the April. So before the final exam, I will make several review classes for you guys to help you guys review the whole course, and you can also send me the topics that you are confused about. So I will talk about these topics in the class. Okay, and also after tomorrow's class, I'm sorry, after the next class, I will give you the homework for this chapter. And after you finish this chapter, uh, we have one more assignment. That is the final exam. And after the final exam, we pretty much finish this semester. Okay. All right. Please let me know if you have any questions. And um, have a good day. See you guys.